Okay. On Friday, we talked about doing ANOVA for a single factor. So I had one thing I wanted to know, did this affect some numerical value? Now I want to expand this. We can talk about multi-factor ANOVA with just about any number of factors we want. But the more factors we have, the more complicated the model gets, the uglier the actual math gets. And most of the time, we really don't ever get bigger than 2. But even 2-factor ANOVA comes in 2 varieties. We can talk about 2-factor ANOVA without replication or with replication. We're going to start on the without idea. I've got 2 different things I think affect Y. Friday's model, we had which station we were at a box producing plant. And that was our factor. So I've got some choices for A, like I could have different stations in the room, but I also have different shifts, different crews. So I could think of, let's look at which shift as well as which station. Well, then I have choices for both of these. And I've gone through to R and C for row and column. So there are however many choices there are for factor B, however many choices there are for factor A, whatever these levels and groups are. The without replication idea means that each of these combinations of factors, each treatment, has one observation. So there's one observation here. First row, first column. One observation there. For each row, there's one and only one number. Some people call non-repeated measures. There's only one measurement in each combination of factors. So let me see if I can parallel the idea that we came up with on Friday. If I'm lucky, my null hypothesis, what would my null hypothesis be when I look at what effect each of these treatments has? Comparing averages. So I'll get an average for each column, I'll get an average for each row. There's a dot there on purpose to indicate that that is for the row and no column number. Down here, I'll have y dot 1 and y bar dot 2, and I'll get y bar dot c. And then overall, I'll have some big grand average for everything. So these are averages by column. These are averages by row. This is my grand average. In parallel with what we did on Friday, what was my assumed null hypothesis on Friday? I only had one factor to worry about. We even wrote it as a capital T on Friday.
The effect due to the treatment.
The effect due to the treatment. That was our capital T. What was our null hypothesis on the effect due to the treatments on Friday?
If there is no difference.
That effectively all the treatments cause no difference. There's just one grand overall average, maybe a little bit of random error, but the treatment should have no effect. But now I've got two different factors contributing to each treatment, right? So here I'm going to say, okay, there should be no effect from which row I'm in. That all of the A treatments cause no effect. And there should be no effect from which column I'm in. Which means when I do two-factor ANOVA, I actually have two different null hypotheses. One for the rows and one for the columns. So my null hypothesis for the rows will say that which row I'm in doesn't matter. In other words, the treatment on my linear equation idea, that's where those T's were in the linear equation. That the effect of the A part in the linear equation is zero. If we think of the AR like we did our T's on Friday, we had T1, T2, T3, and they all might add or subtract something to this overall mean. I want to say no, the thing we are overall adding to this mean should be zero. If that's my null hypothesis, what's the corresponding alternate hypothesis?
It's not zero, so it's
Say again?
The effect from AS is not zero, so it's not equal.
Yes, the effect is not equal, but it just means at least one of them, right? Doesn't have to be all of them. It could be one, it could be more, but at least one of them has an effect. That's different. I'm going to have the exact same pair of hypotheses for the columns, not column. Column is the mark I made over there. What is the column version of this? How do I change it?
Can you see the thing?
How do I change this to match the columns? The only thing I want to do is change what I'm looking at for the rows to now say, let's apply this to the columns as well.
You just have to put B.
That's it. Place the A with a B. Now, since we think of ANOVA as trying to make a line, the Y value, the numerical value we are looking at, I was looking at number of boxes packed at each station on Friday. I could say the number of boxes either does or does not depend on the station. We decided on Friday that it did, I think. But now I can also say the number of boxes packed at each station does or does not depend on which crew I'm using. Two different factors, two different results, two different F's, two different P's. My ANOVA calculation is going to happen the same way. Big, long, a lot of algebra measuring the effect on the averages. That's why I have those Y bars and the grand average up in that table. If my linear model says we have some overall big average in my population, then there's some effect caused by all the J's, all the A's, some effect caused by all of the B's, and then some little random bit of error that might depend on each treatment. If my null hypothesis is true, then all of the A's contribute nothing, and all of the B's contribute nothing. And any variation is due to random error. That means there's no effect from which station we're at or which crew we're dealing with. That would be ideal, right? That all of my stations are equivalently capable of helping people pack boxes, and all of my crews are equivalently good at packing boxes. And there really isn't a difference. Whether you send this job station 1, 3, or 5, and whether you, 1, 3, or 4, because you only have 4 stations. And whether you send it during day shift, afternoon shift, or overnight shift. It is possible to have the results of my ANOVA tell me that the rows do matter, but the columns don't. Or vice versa, that the columns do matter and the rows don't. So maybe which station I'm at matters, but which crew doesn't. Or maybe it's the other way around, and which crew I'm using matters and which station doesn't. Or both of them could have an effect, or neither of them. All of the options are on the table here. But what this means is I'm going to get two different probability results. I'm going to get a p-value for the rows, and it's going to tell me whether or not which row I'm in matters. I'm going to get a p-value for the columns. Same deal. Questions? The example on page 428 talks about paint. I look at how easy or not it is to spray the paint I'm using, how thick and gloopy it is, the viscosity. And it could be affected by the temperature. It could be affected by the supplier. So I'm going to have row factors, column factors here. And I take one sample from each supplier at each temperature, and I spray it and I see what it looks like. Question?
So, in order to not reject H0, they have both to be true.
I can do each set of hypotheses separately from each other.
But they have to look at both.
I do have to look at both. But I can say I reject H null for the rows because the p-value is small. I accept H null for the columns. I don't have enough evidence to reject it. So it could be that I get one or the other, or both, or neither. Okay. You're welcome. Sometimes we really have only one of these factors that's important, and the other one is there as a control to try and break us from the influence of other variables. For example, it might be that I don't think temperature matters all that much, but the supplier of my paint matters quite a bit. Well, then I'm using temperature kind of as a red herring. I don't care what the temperature effects are. I care about whether or not there's a supplier effect. We really call this a randomized block model. In DT 100, you should have heard the idea of a confounding variable. We talked about correlative behaviors. We looked at things that went together. We'll talk more about that in a little bit. But I could ask the question, does ice cream sales cause drowning? If you think about it, there are way more drownings when there are way more sales of ice cream. I can show you that those two things go together. You have a lot more drownings when you sell a lot of ice cream. You have very few drownings when you sell very little ice cream. Why?
Because of the summer, we go swimming.
It's summer, we go to the beach. There are a lot more people swimming, there are a lot more people eating ice cream. In the middle of winter, we stay the hell away from the beach up here, right? So, yes. So there's really an underlying outside influence to both of those things. A confounding variable. It's the temperature or the season. whichever way you want to think. In this case, I really think of only one of my two behaviors as mattering. And I'm gonna put those in the columns most often. And the phrase for that is to think of the rows as the blocks. And that means I randomly assign each group in the row to the treatments. So I have a little bit more randomization in each row. But I should still have one thing here. That's what that randomized block model means. Within the row, you randomize, shuffle those up. The only difference is in the interpretation. Now, Alessandro, now when I look at this, I really only want to know what the second factor does. I want to know what the columns do. Columns were my B's. That's really the only one I care about. I don't care all that much whether or not there's a row of. So I'll still do the exact same set of calculations. I'll still do the exact same reaction. The same maneuver I'm going to do in Excel. The difference is that I'll interpret it like it was a one-factor ANOVA. By the way, the result is ridiculously common. Page 430. Holy moly. The only reason I show you all of this calculation is to show you the rightmost column. This is what matters. When all is said and done, I'm going to look at the total of the variations in the row, and that's going to take those row means. I'm going to look at the total variation in the columns. That's going to take the column means. I'm going to use my degrees of freedom. I'm going to look at the total overall error. And then I'm going to end up with two F values. If I get two F values, I get two P values. I get two potentially different conclusions. Now, again, I have never done ANOVA by hand. I don't plan on it anytime soon. But that means what I need to do is set up the problem and then interpret it. So here is problem 21 on page 433. Concerned about Friday absenteeism. Management examined absenteeism rates for the last 3 Fridays in 4 different plants. Does this sample provide sufficient evidence to conclude that there is a significant difference in treatment means? Okay, wait a minute. What's a treatment? I can't interpret the question. I want to know about differences in treatment means. What's a treatment? In a randomized block model, yes. But in general, it's not just a column, it's a combination of row and column factors. If I was really only concerned about one of these things, then somewhere in here, I'd have to say something about a randomized model. Since they didn't actually say that here, I'm going to assume they want both to know about row effect and column effect. So I've got 12 different measurements. How many people were absent from each of the 4 plants on March 4th, 11th, and 18th? Is there a difference in absenteeism based on where we are or based on which weekend it was? Let's find out. Here is the data file for our, that's the wrong one. Here is the data file for our absenteeism rate. Helps if I have the right Excel sheet show. Okay. I'm going to do the data analysis tab. Go grab this file off of our class examples. If you've got your computer with you, jump to our Canvas page, pull this sucker up. Chapter 11, Section 5, question 21 is what it's called. The file name is absences. So, before I do any math or any clicking in Excel, I need to know what I'm looking for. What is my set of hypotheses?
Like March 4th, March 11th, and March 18th are equal to 0. I mean, plant 1, the column.
The columns, the rows, that column of different rows. It's not that the days are equal to 0, but that
Not what?
the effect from the different day is 0. So there's no difference based on which week it is. So that's the first null hypothesis. Whether we're on March 4th, 11th, or 18th shouldn't matter to the number of absences. What's the alternate that goes with that?
That it matters.
That it matters. At least one of them will give me a different result than the others. But that's only one set. There are 2 sets of null hypotheses. What's the other set?
And the effect doesn't change also based on the plants.
Exactly. That it doesn't matter which plant I was at, plant 1, 2, 3, or 4, all have the same effect on my overall absenteeism rate. So, under data analysis, I want to do an ANOVA. And notice we're back at the top. There are 3 options for ANOVA. The one we were doing on Friday was the single factor. But there are 2 under 2 factor. Which one do I want?
We are doing it with the replication.
Are we with replication here? How many observations do I have in each treatment? I only have 1.
So without.
So I'm without replication. The replication refers to the fact that I have 1 observation from plant 1 and March 4th. And 1 observation from plant 3 and March 18th, right? 1 observation per treatment. No replication. The way I was taught this was actually not to use the word replication, but repetition. I only took 1 measurement from each treatment. So there's no repeated measurements. So I'm going to go without replication. Click. Okay. Input range. Oh, wait a second. There. I don't want to actually catch the title. location. I just want to catch the dates and the plants. So I want the labels, and then I hit enter, and I'll tell it, hey, I got the labels. That way it'll label the rows and label the columns with the right names. I'm going to pick my same old alpha 0.05. Again, if I thought this was a looser significance would be better, I could do 0.1. I could do a tighter significance. I really want to know if there's a difference. I'm only going to accept it if it's 1%. It's got to be really outlandish of an effect. The smaller alpha is, the harder it is to reject my null hypothesis. Click OK. It's going to stick this in a new worksheet. Bang. Here is all the data this thing gave me. Oh, joy. What the hell? What's it all mean? I got a lot of information here. So now the question is, what are the answers? Based on the question I was asked, does this show a difference in treatment means?
The alpha is 0.05.
0.05. You'll notice that doesn't show up anywhere on here, does it? So I have to have that somewhere else. I have to have that information given to me at some point. As a matter of fact, in the textbook, when we were looking at all of these problems, it says in the instructions to use alpha equals 0.05 for all of them. So I'm ahead of the game, but I have that alpha, but I need to remember it because I don't see it here.
But now that we know alpha, we can just compare the p-value.
Exactly. I have two p-values. Those two p-values are here. Based on p-value that goes with the rows. What does that tell me?
But we have to reject those rows and columns.
I have to reject both rows and columns. The p-values are both smaller than 0.05. So now let's answer the question they were asking. Does this evidence demonstrate a difference in treatment means? That's a yes/no question. What's my answer?
Yes.
Yes. Since I rejected both null hypotheses, both which plant I'm at and what date it was at. There's a difference both ways. If I was doing a randomized block model, then the treatments would be the columns. In that case, I would be like, oh, well, then the treatments are which plant matters. And I don't care about the date. I just care about which plant. Now you'll notice which Friday it is versus which plant I'm at. Which one of those matters more?
Columns.
And the columns represent?
No, that.
This is why I have the data. Columns represent the plants. So which plant I'm at matters more because that p-value is 0.0002. It's smaller than the p-value from the rows, 0.017. So which column matters more than which row? Wonder why that is. This doesn't tell me about cause. I don't know why which column matters so much, which plant. I don't know. Which plant had the highest average absenteeism? It looks like plant 3, where the average is 29. Maybe that's right next to a bar. It's Friday, I'm out. Or maybe there's some other reason, but I have no idea what the cause is. Just that there's some effect here. Like show isn't just randomness. But I can say that both which plant I'm at and which weekend it was affected absenteeism. Questions? Question number 23. Driving time from the airport to each of 4 downtown hotels is recorded for 5 Uber drivers. Does the time to get from the airport to my hotel matter based on which driver or which hotel? All 4 hotels are, quote, downtown. All 5 drivers drive for Uber. Does the choice of driver or the choice of hotel matter? If this were a randomized block, which is the actual treatment and which is the random factor? Which are my blocks? Which are my treatments? Because that's my column effect. And my rows are the blocks. So I would take these drivers' times randomly, quote unquote, not caring which hotel they were going to, right? I don't care about the hotels as much as I care about which driver it is. Let's see if the driver has an effect. Let's see if the hotel has an effect. Let's see if neither of them have an effect. I lost the mouse. There it is. Wrong one. I can't actually share the file until I open it up. Okay. Grab your computers, please do this. Under examples for class, this is chapter 11, section 5, question 23.
But mine was already done.
I'm sorry?
Mine was already done.
Oh, that was convenient. So I upload it with the actual completed stuff.
I don't know.
That was nice of me. So we run through the ANOVA, data, analysis, two-factor, highlight the right pieces.
I don't know.
There's our data. In the upper left here. And here's the results for our ANOVA without replication. If this is randomized block, I only want to know if the driver matters. Does the driver matter?
No.
No. But look at that p-value. Column's p-value is 0.050006. I don't think I could have made this any closer of a call, right? We're supposed to reject if the p-value is less than 0.05. This is just barely bigger than 0.05. I mean, it is 6/10,000ths, right? No, 6,000ths. 1, 2, 3, no, 10,000. 6/10,000ths of a percent. By the skin of our teeth, we are not rejecting this null hypothesis. No, drivers don't matter. I would wager that if we had more information, perhaps more samples per choice, per driver, then I might actually be able to show something did matter. What about which hotel we're going to? Does which hotel we're going to matter? Why not, Pete? 0.38 is much bigger than 0.05. I don't have to worry about which hotel I'm going to. I must tell you that I learned a lot from an ANOVA. More than if I did individual t-tests. And I could ask further questions about whether or not there were any particular effects, just like I did with the one-factor ANOVA, only I didn't actually do it for us, because there are other tests, Tukey's test, Haney's test, there are other tests that will allow me to do a deeper dive, but I could also then just look at my averages and say, yeah, there's some variation here, but is it enough to matter? And that column 3 average being 30.25, all of the others are 25, 20, oh wait, but there's another one that's at 22. So it's like there are 3 in the middle and then one outlier above and one outlier below. So I might not be able to say that overall my driver choice doesn't matter. Driver E versus driver A. Sorry, column 5. Driver C versus column 3. Yeah, driver C versus driver E. Those are the ones that are going to matter. 22 to 30. That's a pretty big window on average. Question. It might be worthwhile to graph these as if they were line graphs. Graph across each row, graph down each column, and get a visual and say, oh, I want to look at drive time based on driver, drive time based on hotel, and look at my 5 or 4 dots going across and see how those lines look to each other. Remember, we're talking about our one factor. I said you could look at whether the lines crossed or not. Might be worthwhile here as well. Questions? Okay. I will talk about with replication on Friday, because on Wednesday, we have the exam. 2 reminders. You get another formula sheet and all the tables. You use the formula sheet from the last exam. And you will be expected to at least do some of these calculations by hand, compared with the calculations that are on the review sheet. I won't expect all of them. Notice on a bunch of those, I gave you results from Excel. So you'll see some of these all done out for you. Some of them you will have to produce. It's why you get the formula sheet and all the calculation stuff, you can write down all those formulas. I will see you on Wednesday, I will post the review sheet key, the answer key to chapter 10, the other homeworks. Have a wonderful rest of your day.